It's what's the best.
Yeah.
We could put a photo of it. All of that is getting recorded. That's fine. If you want to go into something,
Yeah.
there's a point.
Okay.
And if you want to drink, you can
Okay, thanks.
take the bottle. And we finish anyway.
Okay, the mic is working, I think. Yeah, I think I hear my.
So we're gonna have two talks in this session. Before we go move on to the talks, maybe one announcement. Right after this session, we are going to have a conference in photo on the backside of the main building, so this building. So we're gonna meet there at 12:15, I believe, because the other session has three talks. And we're gonna show you where to go, so. Now, let's start with the talks. The first talk is going to be by Yasun Setoglu, and the title, A Wall Model Hybrid LBM for Compressible Flows.
So, thank you very much for the introduction. As you heard, I'm a postdoc at M2P2 lab, and my topic is a wall-modeled hybrid LBM for compressible flows. To give a bit of context, as you probably already know here, LBM has proven quite an attractive alternative to the usual simulation methods due to its simple mesh generation and its very good performances in parallel architectures. In our lab, we co-developed the code ProLB, which uses the unified hybrid recursive LBM model to a wide variety of applications, both industrial and academic, for high Mach number flows, external aerodynamics, combustion. However, there's still some more work to do with aerothermal studies in internal compressible flows. Such flows could be the first stages of the turbines in modern aircraft engines, where high pressure, high temperature gas arrives at the blades where it accelerates rapidly, creating probably shocks and high temperature gradients. Now, to study these effects, we chose a simpler case. It's the experimental cascade from the von Karman Institute, the LS89 cascade, which is widely known in the CFD community and has a wide range of data set to compare. Thus, more specifically, the topic of this presentation is going to be the objective is going to be to extend the applicability of ProLB to internal compressible flows for aerothermal studies. And we're going to implement the unified HRR model coupled with velocity and temperature wall models to the LS89 cascade. And we're going to mainly look at aerodynamic and thermal quantities near the blade and the prediction of the shock position. And recently, we also incorporated some temperature wall models to better estimate the heat flux. So this presentation, I'm going to, first of all, explain a little bit the ingredients of ProLB. Then we'll move on to the test case, the results, and then we will conclude. So ProLB uses a hybrid LBM methodology where the mass and the momentum equations are solved with a lattice-Boltzmann solver. However, the total energy equation is solved by a finite volume scheme. For the lattice-Boltzmann solver, we use a modified D3Q19 lattice with a unified fourth-order equilibrium for compressible flows. For the collision kernel, we use a hybrid recursive regularized model. And for the boundaries, we were inspired by Katzel immersed boundary treatment coupled with wall models. And for the total energy, for the finite volume scheme, we mainly use Massel-Hancock for the flux reconstruction. And we're going to see later, it's a bit modified equation, actually. So I believe I can pass a bit fast these two slides. Everyone here knows the Maxwell-Boltzmann distribution of equilibrium, where in a small control volume you have this probability density function for particles to follow for a given mean density, temperature, and velocity, which we then project onto the Gauss-Hermite polynomial base to actually have it discretized over a set of velocity directions. Now, using these equilibrium populations and the off-equilibrium contributions, we have the current population Fi at a given place and time. And we use the discrete velocity Boltzmann equation to actually model the evolution of these populations, which, as probably everyone here knows, we're going to separate into the propagation step and the collision step. So this is the usual algorithm for a lattice Boltzmann. I think everyone knows it. So more specifically, in ProLB, we discretize the discrete velocity Boltzmann equation with a Crank-Nicholson scheme, which is implicit. So for that, we use an offset numerical population, F bar, to make it again in an explicit formulation. And from that, we get a new offset of equilibrium population and a new collision BGK collision operator. And finally, we have the discretized form given for F bar as such, with a new relaxation time, tau bar. Then the unified HRR model. So for the equilibrium, we used what we have recently developed as the unified equilibrium model, which is basically the same as the usual density models. However, if you can see the second term we added, and this takes into account the thermal effects for compressibility reasons, and it's equivalent to projecting information onto a fourth order, into the fourth order. For the collision kernel, we use the hybrid recursive regularized one. Hybrid because for the second order moments, we actually used the lattice Boltzmann contribution. However, we also implemented a small portion of the macroscopic shear stress contribution, which was discretized with a second order central finite difference scheme. So this artificially added some hyperviscosity into our model, making the simulations more stable. And for the rest of the study, it's going to be set the sigma factor as 0.97. And why is it recursive regularized? Because we regularized it at the third order, but it's found the moments by the second order ones, so recursively. So I will not repeat too much of the algorithm since it's pretty standard. However, at the end, we also have to add, once we have the new macroscopic quantities, we're also going to advance the energy equation to find the new temperature. So to do that, we use a finite volume scheme. Now, historically, usually in ProLB, we use the entropy equation due to its simplicity to decouple from the mass and momentum, due to it being a characteristic. However, Gauthier-Vissoc recently introduced a linearly equivalent scheme for the total energy, which is a modified version. It takes into account into the intercell fluxes, actually, the lattice Boltzmann mass and momentum fluxes to restore a consistency between the two different discretization schemes and solve some conservation problems that we had. Now, for the boundaries, as I said, we're inspired by Katzel immersed boundary methods, where we have our boundary nodes just outside of the solid. To actually impose the boundary conditions on the boundary nodes, we first need the near wall values interpolated at the reference point, usually 2 or 2.5 delta x from the wall. And then, with the information at the reference point and the wall, we can find through Dirichlet, Neumann, or wall models, the actual boundary condition we need to impose at the boundary node. The velocity gradients are simply computed with a finite difference scheme. And for the populations at the boundary nodes, we reconstruct them through this equation, where the equilibrium is simply found from the macroscopic quantities, and the off equilibrium, it's also from the macroscopic quantities from the shear stress tensor. So how do we actually find in this study the boundary node the value at the boundary nodes? For the velocity, we used the explicit power law velocity model, where, as I said, we computed u tau, for example, at the reference point, and then following the power law, And based on the y plus values, we determined the boundary node value of our velocity. We did something similar for the temperature, where we introduced the Kader logarithmic law. Once again, t tau at the reference point, and we also computed the Q wall, the heat transfer to the wall, from this reference point. And then the boundary node, the value at the boundary node. And to finish with the modeling of ProLB, for the viscosity, we used the Sutherland model for the molecular contribution, the Vreeman turbulence model for the subgrid scale contribution, and we also added a Jameson-like shock sensor to better capture shocks. And this is going to give us now the new modified relaxation parameter tau bar. So let's move to the test case. As I said, we're going to look at the LS89 turbine cascade. For this, we took two distinct cases, a subsonic one, the MUR 1 to 9, and a transonic one, the MUR 47, where we're going to have a shock appearing. And you can see the isentropic Mach number at the exit is 0.8 and 1.2, 0.2 respectively. However, it's still two cases with low free stream turbulence intensity, so it was omitted from the actual modeling in the simulation. For the domain, it was created simply with an octree mesh, as you can see, a Cartesian grid. And I chose three different refinement levels, 0, 1, and 2, which are actually pretty coarse near the blades. We have from 130 to 540 points per chord. But this corresponds well into the logarithmic region if we take the average y plus over the profiles from 150 to 50. And for the boundary conditions, we use the total pressure and total temperature inlet, the loaded pressure outlet coupled with the viscosity sponge zone, and the rest of the boundaries are periodic, except for the blades, where we use the wall models to impose the non-slip condition to the velocity and an isothermal condition to the temperature. So let's move to some results. In the subsonic case, first of all, we need to verify the exit flow conditions that match well with the experiment. So we compared the isentropic Mach number and the corresponding Reynolds number at the same probe location as them. We can very well see that it is periodic, thankfully. And if we look exactly at the mean values and the relative error compared to the experiments, we're in the ranges between 0.5 and 2%, which is very good for the coarser grids that we are going to use. Taking a closer look now to close to the blade, we have this isentropic Mach distribution, where we can see that for all different refinement levels, we have very, very good results, and they match perfectly with some wall-resolved LES done by Segui in 2017. And for the levels of refinement 1 and 2, we're almost identical. And we're going to see the same for the transonic case, the MUR 47, where we're supposed to find the shock. So for the coarsest grid, n equal to 0, unfortunately, it's too coarse. We didn't capture well the shock, nor at s equal to 20, the area where we have the high curvature. However, for n equal to 1 and 2, we find perfectly the position of the shock. And if this graph doesn't convince you, I've also plotted the mean density gradient fields and compared to some experimental images given in the report of arts. You can see very well that not only did we predict correctly the position of the shock, but also its form, or rather deformation, due to the influence of the wake of the upper blade. So very good agreement overall. Now, passing to the heat transfer study, it's going to be only in the subsonic case, where, as I said, we have the thermal heat transfer QW directly from the wall law. And then we're going to compare the heat transfer coefficient for the three different refinement levels. Now, you can see that generally we have the good behavior in all of the different grids. However, for n equal to 1 and 2, we have the best estimations corresponding to the experimental values. One problem is that we observe compared to the velocity model that this is quite more sensitive to the different grid sizes and the y plus value. Although I admit that this is a work in progress and it's still an open question, whether it's more related to the y plus value of the boundary node that I show here, or rather at the reference point, where you can see that, for example, for the coarsest grid, we have y plus values quite high actually. And now I would like to pass to a final word about the code and its performances. For across all the different simulations I showed today, yeah, if we compare the reduced computational time, that means the time taken for each iteration per computational node, we stay relatively constant between 2 and 3 point something for microseconds per iteration per node, which is quite high performance if you see some other finite volume codes, for example. But that's the pros of LBM. So, and also you can see that, of course, I try to keep the same number of processors, the same number of iterations, and you can see that the CPU hours also stay relatively moderate. Now, from that, we're going to pass now to the conclusion and some perspectives. So during this project, our objective was to extend the applicability of ProLB for internal compressible flows with our thermal studies. We did that by applying the unified HRR LBM model, coupled with velocity and temperature wall models. Applied that to LES simulations of the L39 cascade, we were able to actually predict very well the aerodynamic, some aerodynamic quantities, not only at the exit flow conditions downstream of the blade, but also near the blade. And more importantly, also, we predicted perfectly the shock position in the MUR47 case. For the heat transfer, we're still working. We saw that overall we have very good estimations relative to the experiments, but there's still some improvements to be made. But overall, with just 270 points per chord, which is quite coarse, we're able to have sufficiently accurate results in both aerodynamic quantities and the heat transfer and the heat transfer. So some perspectives, of course, improvement in the temperature model. We're to better assess the validity of the Y plus range. And of course, the possibility to couple it with runs modeling near the wall, which some preliminary studies showed some better results. And for the future of this project, we're also going to apply this method to more complicated cases with turbulence injection and 3D effects. And with this, I would like to conclude my presentation. And if you have any questions, please feel free to ask. And thank you.
Thank you for your talk. How do you compute the non-equilibrium population by the wall model? You have shown that you reconstructed with the gradient of velocity.
Yeah, basically it's, I mean, let me find it. Basically, if you look, it's only with the second order term, but the macroscopic shear stress. So basically, it's just the A2 of equilibrium finite difference, just from that formula projected onto, yeah. So basically, just the first term of the F of equilibrium. This, but with sigma equal to 0. Yeah. You're welcome.
Yes, just a very basic one, not in the shock wave field. So could you just tell us about the basic physics of those blades and why the shock wave is, why it isn't, why it's periodic?
Why? Sorry, why?
So you showed these periodic shock waves going through the.
Yeah.
I wasn't quite sure why you got not a continuous movement, but periodic shock waves in there.
It's simply related to the experiment. It was a linear cascade. So it's not the real cascade where you have, for example, the annular geometry. So it was linear. So you can see basically the same physics exactly at each blade, and it doesn't influence too much the next blade, except for some small parts that are mostly related with aeroacoustics. But if you see some points here at the trailing edge of this blade, it influences a little bit the values here. But overall, at the shock position, it's not affected too much, just the wake where it deforms. So that's why it's the same.
But so they have to think about these plates moving at a constant speed?
No, this is in a stator state. It's not moving, and there is flow coming from the left in the horizontal. Yeah, it's before being fed to the rotor. Yeah.
And you showed the heat transfer results.
Hmm?
These were results measured on the wall of the plate, right?
Yeah, through the boundary nodes, on the boundary nodes. Yeah.
The last like lattice side, not occupied by solids, right?
So basically, at the boundary nodes, on the last nodes of your mesh, we don't actually solve LBM. So on the first layer of nodes around the blade, as I said, we computed through the immersed boundary formulation, let's say, and we've reconstruct effective post-collision populations to then use them to the rest of the nodes. So basically, yeah, the heat transfer is computed from. Okay, I will take it back. Actually, it's computed from at the reference point, if you remember, where we interpolate values. Yeah, it's more in a macroscopic, let's say, view, and not directly computed from LBM, if that explains some stuff. I don't know. Yes.
You have a wardrobe, so you have a gradient far away, and then you use the wardrobe and then get your cross right on.
Is that virtual? Yes.
Yeah.
That is actually on the wardrobe.
Yeah. And at the boundary node, of course, you take, due to the temperature gradient, you can compute then the new temperature at the boundary node, and it appears in the equilibrium part.
So, questions? We can thank the speaker again.
Thank you.
So it is going to be a talk about throwing double distribution function models and the methods for by
Right, just a second. Just get started. All right. Morning, everyone. Thank you for attending my talk on probing double distribution function models and the lattice-Boltzmann method for compressible flows. Let's get started. Right, so compressible flows, as we all know, as the last talk also demonstrated, are very important to everywhere in science and engineering. Extension of regular LB, standard LB, to compressible flows has been a relatively well-researched area of study. There have been many different ways people have recommended doing this. The simplest one being basically just using higher order lattices to do this, but that comes with this additional computational and memory footprint that we probably don't want. Another simple extension to make LB applicable to compressible flows is with the addition of an additional population that we will use to carry effectively a form of energy. And this allows us to simulate compressible flows while still keeping relatively smaller lattices. However, the choice of what form of energy to carry on the G population isn't really unique. There have been several different ways that have been proposed. And that is the focus of this study. We basically probe 3 different ways that have been proposed in the literature to handle the second distribution function. And we see how it affects the simulations, for example. So getting started, For a double distribution function, we need the first distribution function first, and that's the usual one, nothing changes. It conserves the mass and the momentum at the 0th and the first order moments as expected. Nothing new here. This is where some of the interesting stuff happens. So we introduce a second population. Quickly just introducing kinetic energy, K, internal energy U, total energy E, and the internal energy with just the non-translational degrees of freedom U prime. That gives us three different ways to sort of now split the internal energy. Just a second. To split the energy on the G population. So we have three different ways. So the total energy split, what we will call in this work, in which case all of the total energy is on the second population. The internal energy split, where it just carries the total internal energy on the second population, and the total energy is that. And what we're calling the non-translational internal energy, where the second population only carries the internal energy with the non-translational degrees of freedom. So we have these three splits that we're going to focus on. We carried out a multi-scale analysis on this, and we notice that after we do the multi-scale analysis, first thing we notice is the F population, like I said, it doesn't change. So anything to do with the Navier-Stokes mass and momentum conservation doesn't change. We recover the mass and momentum conservation correctly, irrespective of any of the three splits that we use. The TNS being the viscous stress tensor here, and eta is the bulk viscosity. We also see that irrespective of the energy splits that we use, we do recover the connect energy equation as well, with certain caveats, and we will be focusing on those caveats. Another note here is that since we're focusing on just the effects of these three energy splits, we stick to a simple single relaxation time model that sort of limits us to Prandtl number of 1. But this can be easily extended using something like a quasi-equilibrium approach to change to tune your Prandtl number. Did that change? I didn't. Right. Right. So now we have, again, once the splits with also the collision terms here. First note you might notice for the internal energy split is that the collision term now comes with an external source term. This is a model that was first proposed by Hay, Chen, and Doolin in '98. This comes with an external source term, with a separate source term that has derivatives both in space and time. So that might not be ideal for locality. We will also see that later. Another note here, and a more important one, is about the order of quadrature and the lattices that you need to recover the Navier-Stokes equations, which I said all the three models do correctly. So for the total energy split, the F population needs to properly recover the continuity and the momentum balance to the Navier-Stokes level in the Chapman-Enskog expansion, which involves equilibrium moments up to order 3. And the G population needs to be correct up to the order 2. So what this effectively means is that for the total energy split, a D1Q4 lattice in 1D or in 2D, that's T2Q16, would be sufficient to recover the Navier-Stokes Fourier equations. We could also do with D1Q3 if we add correction terms. For the internal energy split, the situation more or less remains the same. The D1Q4 lattice, that's fourth order quadrature, is sufficient to recover the full Navier-Stokes Fourier equations. But the change comes for the non-translational internal energy split. So we have, so here, if you notice that the total energy is equal to the 0th order moment of the second population and the second order moment of the F population. For this to work correctly to recover Navier-Stokes Fourier, we need the the first population moments to be correct to order 4. And that means that we need a 5th order quadrature to correctly recover the Navier-Stokes Fourier equations correctly. So for the rest in the study, we will do simulations depending on the situation with both D2Q16 and D2Q25. So that's D1Q4 and D1Q5. Quick note on the discrete velocity solver that we're using here. So we're using particles on demand. So that's the model that we developed in our group for simulating very high-speed compressible flows. The primary difference here between pond, as we call it, and standard LB is that we have adaptive reference frames here. So each lattice node in the whole domain has its own unique reference frame, which is defined with its local velocity and local temperature. And the discrete velocities, instead of being fixed by the lattice, are completely adapted, like so. What this means practically is that our model is now completely Galilean invariant. The reference frame, like I said, is completely adapted to local flow, which makes it a co-moving reference frame, as we call it. It really removes any restrictions on Mach number and temperature gradients, so we can technically simulate arbitrarily high Mach numbers. The one downside this brings with us is, since the lattice is no longer space filling, it's off lattice, and we need to deal with that somehow. And also we get exact equilibriums because of our frame being locally adaptive. Our equilibrium is exact, so you can see Fx is basically only dependent on the density and the weights. So for off-lattice advection, we use semi-Lagrangian advection, tried and tested method, with one change. So as I mentioned, at each local lattice node, the reference frame is unique to that local lattice reference node. And this changes at every time step. So a simple interpolation using semi-Lagrangian will not work, because if you see on the figure on top, so at our departure point, the point 0, we need 4 points around it to do the interpolation, but each point has its populations defined in its unique reference frame. And for consistency, we need to make sure that all these reference frames are correct, are identical. So we need to transform them from each of their reference frames. So in this case, the lambda 1s, the lambda 2 are the reference frames, and we transform them from their local one to a common reference frame before we do the interpolation. For this, we make use of frame transformations and the property of moment invariance, which is to say that when the reference frame changes from one to the other, we say that we impose that the moments do not change with that reference frame. We make use of grad expansion for this and to reconstruct these population up to a third order expansion, basically. Most of the information here can be found in the previous papers where we expanded on these transformations. So now quickly moving on to some of the results. So first, simply, we measure the speed of sound. We do it for all the 3 energy splits that we just mentioned. And we measure the speed of sound effect over temperature and for different ratios of CV. The ratios of specific heat ratio, sorry. We have a theoretical solution for this, obviously, and we find that our simulation results, well, they match exactly as what we impose. We basically impose a shock front, and we measure how the shock front moves in space. This works even for D2Q16. There's no need to use a higher lattice. We don't see any difference for D2Q25, even for the energy split that requires D2Q20, the 5th order quadrature for recovering Navier-Stokes equations. Next, to measure the dissipation rates of the 3 hydrodynamic modes, the shear, the normal, and the entropic, we do some simulations. So we start with the normal mode. We initialize a plane dissipating shear wave. So with introducing a perturbation in the velocity. And we measure the maximum temperature decay in the field. We know from literature that it should be exponentially related to the shear viscosity. And we basically do some curve fitting, and we arrive at the viscosity that is felt by the fluid. And we do this over a range of Mach numbers. And we find that once again, even for D2Q16, the imposed viscosity is the same as the viscosity that is experienced by the fluid for all 3 energy splits. We do the same thing for the normal modes. This is the measurement of bulk viscosity. The perturbation is slightly different here. Now it's a perturbation in density. And now we monitor the energy decay over time, which should, in this case, be exponentially related to the effective viscosity, which in this case, since the shear viscosity is 0, the effective viscosity is a proxy for the bulk viscosity. Once again, over a range of Mach numbers, all 3 splits produce identical results for viscosity, correct as we imposed it. And then finally, the entropic mode. So here we measure the thermal diffusivity. The initial dissipation, the initial perturbation in density and temperature. We measure the temperature drop or change from the initial temperature, once again exponentially related to the diffusivity, and we get identical results to DTQ16, which is also not unexpected. So for a stronger test to assess the proper recovery of the combined effect of viscous heating and thermal conductivity, we consider thermal couette flow. So that's couette flow, but with a temperature gradient. We have a stationary slip wall at the bottom, a moving wall at the top, and a temperature gradient between them. So the upper wall is at temperature T1 and the lower one at temperature T0. We know the analytical solution. Prandtl number, as I mentioned before, is 1. The Eckert number basically is used to characterize heat transfer dissipation, and that is what we'll use in the two simulations that I show. So we start with Eckert number 8, so it's a relatively small Eckert number. And here, although we expect to see differences, so this is where the non-translational internal energy should break, and we should see deviations. We don't really see it for this test case. They're all identical with the D2Q16 lattice. So this is the D2Q16 lattice again. So we change things up a little. We increase the Eckert number. What that basically means is the temperature and the velocity gradients that we sort of impose are much higher, as you can see. So in the previous slide, the scale of the temperature gradient was up to 1.6. In this one, it's 6-7 times that. And you finally start to see the non-translational internal energy sort of break. On the inset, you can, so it looks like it's coinciding with the analytical solution, but if you look at the inset, you will see that there is a clear variation between the non-translational internal energy. To further, and this is again what we expected, to fix this, we now move to the D2Q25 lattice with the non-translational internal energy split. And what we expect to see is that the move to the fifth order quadrature should fix this error, and we should become sort of superimposed with the analytical solution again, which is what we see. So that again is as expected. One small note here is the fact that all of these temperature gradients don't seem, the deviation from analytical doesn't seem like a lot. A lot of it is because of Pond having these locally adapted reference frames, which reduces the errors a lot. So if you weren't using Pond or an adaptive method, you might see larger difference deviations from the analytical. And lastly, as a demonstration of the very high-speed capabilities of our model and the double distribution function, we do this test case of the astrophysical jet. It's kind of becoming more important as better and better pictures arrive from things like the James Webb Space Telescope. It's a kind of challenging case because you have very high temperature gradients and very high density gradients. So we basically set up this high-speed jet in the domain at Mach 80 in this case, and we let it evolve into the domain. And on the bottom, you see a numerical Schlieren. And on the right side are snapshots of the Mach number, the temperature, and the density at a point in time, essentially. The results are relatively okay. The results agree more or less okay with the results in literature. And literature in this case is pretty much only other numerical studies by different people. But it does show that we're quite stable and it works relatively well at very high speeds. The one thing here that we use total energy split, only the total energy split here. And we use the Vino interpolation in this case for shock capture. Moving on to the conclusion, right? So we analyzed 3 different double distribution function realizations. We carried out a multi-scale analysis of it. And we found out that all of the 3 models considered can recover the Navier-Stokes Fourier correctly, with the added caveat that the non-translational internal energy split requires a higher order quadrature to achieve NSF recovery. This was further confirmed by simulations using high Eckert number flow with thermal couette flow. And obviously, moving from the D2Q16 to the D2Q25 lattice brings with it computational penalties, as I mentioned. So in our case, we saw something like a 60% increase in runtime. Further, the internal energy split that has a source term that has derivatives of time and space also increased runtime by approximately 15% compared to the total energy split using the same lattice. Thank you so much.
I just had a question to the actual physics that you're simulating there. That must have missed something. So you say it's Mach 80,
Yes.
right? But if you look at the information traveling out from the jet, that doesn't seem to be at a very sharp angle. So why is it? So that would suggest that the information in the front is moving it more than the speed of sound.
No, it is. I'm not sure how to answer that. I'm not sure I understand the question correctly.
So I would have thought that the faster speed that things are moving away from the jet would be with the speed of sound.
Uh-huh.
And if your jet is moving with the speed of 80 times the speed of
Uh-huh.
sound, then I would have thought that this wedge information traveling out would be, much sharper. I mean, it seems to be a relatively flat angle, which suggests that if that was the speed of sound that this front is moving sideways with, I'm just maybe just confused. I don't know.
I'm not super sure how to answer that. I mean, from what we see, it's very similar to the results that I've seen in other papers as well. Maybe it's the visualization that's making it wrong. So in this case, the jet diameter is 100. So
So maybe one thing that I could add to this, this is if we think about the time frame that's simulated here, it's relatively short, right? And if you look at what's happening, the distance between the traveling shock in front of the structure over time, as you can see, it's getting closer and closer. And if we continue further with the simulation, you're going to see the angle getting sharper and sharper, and this getting closer and closer to the structure.
It just looks like the stuff moving out to the sides is moving at a comparable, slower, but a comparable speed, like factor 2 or 3 compared to the front that it's moving.
I mean, what I see, if you just look at the distance between the structure, it's getting closer and closer as we move. And what I would say is if we do the simulation for longer periods of time, because this is really short if you think about the actual physical time that's simulated here, we're going to observe this sharper and sharper and sharper angle that you're mentioning. Yes?
Yeah.
What relaxation rates did you use?
Here, so I mean, so we basically have the viscosity is 1e minus 5, and the relaxation is related to that basically. So I don't think I mentioned it here somewhere, but it's somewhere. Do I mention where the relaxation is? I'll have to check somewhere, but I don't think I messed around with that at all. I can maybe have a look and tell you after the presentation. Yeah.
Should be the finite volume world. Consider only total energy. It's very it's the only form that satisfies the relation. It's with the movement of what you expect, or that you check on the shop. Some tube, things like this, with internal energy or translation energy.
We have, so not in this study, but like previously in the things that we have studied, we've found that internal energy split on the G it also gives comparable results to total energy for our case. So with short shock tube and even I think so, yes. With even with the what's the harder test case? I forgot the name of the test case, but we found that it works. Internal energy also works very well for the.
Still, the conservation of the total energy, even though the split is not always the same, you have some internal energy here.
In continuous form, I totally agree. But in continuous form, all of the equations are the same. Internal entropy, total energy, all of that, that's the same. But if you take entropy equation, I'll show you some plots this afternoon. Entropy equation, you have a jump in entropy across a shock. So if you discretize an entropy equation, you get long jumps. That's why in Gazon was presenting something with total energy equation. Otherwise, all of the results are wrong for shock, for instance.
If we move also at the discrete level, still because we have the quadrature, the consistency condition again is that the quadrature here ensures conservation of total energy. Because still the quadrature is on the combination of that
And
energy.
understanding why this is the case in this kind of scheme and not with classical schemes. I don't know if someone has the answer.
I mean, I think the reason we initially, when the first time, first few papers that did total energy split on G, they did it for the same reason that you said, because it's the one that makes sense to.
As one from hyperbolic community, I would just stop it.
So yeah. But I think, yeah. That will, yeah.
Well, then let's take this speaker. I think those who are not here in the beginning of the session, so we said at 12:15, we're gonna have the group photo for the conference, the backside of the building.